Hi everyone. This is part one of a two-part series of lectures that is to introduce you to the basics of diffraction. So the goals for this are first to talk about diffraction in the context of color. So we'll talk about the optical phenomenon known as iridescence, and then we'll extend that a bit to talk about more specifically about diffraction of visible light. And then just review, since all of you would have heard this before, the wave-particle duality of light, and in doing so, create what will be the basic simple model for diffraction that we're going to use for the next lab in the course. So just to remind you how this ties into what we covered up until spring break, which was talking about crystal chemistry and periodicity, I've included here the example of sodium chloride, which is the mineral halite, but it's just everyday salt. And so what you see in the middle image there is very familiar. It's an expanded unit cell diagram of the halite structure. You can tell right away that halite is a cubic structure. And then on the left there, you see a very well-formed salt crystal, which in this case is in the form of a very nice cube. And as we talked about previously, that equilibrium crystal shape, which in this case is a cube, matches exactly what you would expect based on that cubic crystal structure. On the right might be something that you've seen before, maybe not. It's a X-ray diffractogram. This is a very old one. You can see it's more than 100 years old. In fact, it was one of the first X-ray diffraction patterns collected from any material. And this diffractogram is from a salt crystal that was passed in front of an X-ray beam. And the interference pattern that was created by the X-rays interacting with the crystal structure, specifically the electrons in the structure, is shown there with the dark spots. So, and this is basically a photographic film that recorded the intensities of the X-rays. The very bright center spot is the sort of overexposed area of the film where the X-rays that were passing through the crystal, actually, many of them, most of them, were completely unaffected. And so they just passed straight through, came out the other side, and created that dark spot, which is very intense in the center of the image. The halo of spots around them you can see is not random in terms of the positions of those spots. Those are diffraction spots created by the halite crystal structure. And so just again to sort of tie together the shape of the crystal there, the cubic crystal structure, and what we see in this diffraction pattern, I'll just highlight the relationship between some of the spots with respect to one another. And so here you can see if I connect these four spots, I get a square shape. So obviously the corresponding with one side of a cube, right? And there are other sets of spots I could connect in similar ways. So in other words, the diffraction pattern then is an expression of the underlying crystal structure. So we'll start with talking about iridescence, just to get a handle on a couple of the basics of diffraction. So something which is iridescent has a surface or surfaces that exhibit metallic-looking, intense shining colors that can change noticeably when you view them from different angles. And so examples of iridescence are many, but you've probably seen beetles that are iridescent, like the one shown here. There are also plenty of inorganic structures that can display iridescence, whether naturally or by design. Here you're looking at a crystal of synthetic bismuth, so bismuth metal that was grown and creates this unique step-like morphology, but perhaps more noticeable than that is the bright iridescent colors. So in either of these cases, the origin of the iridescence is caused by diffraction, which is sometimes referred to as coherent scattering of white light by transparent or semi-transparent surface or subsurface periodic structures. So there's a lot in that sentence. We'll show some examples of what's important in the coming slides. Just remember, white light means polychromatic or made up of many different wavelengths or energies of light. Transparent or semi-transparent, I think, should be obvious. Light can pass through to some extent. And then surface or subsurface periodic structures just refer to whether the interaction is happening right at the interface or at maybe various interfaces below the surface of whatever has this iridescent quality. So perhaps a simple example we could use is iridescence that comes from soap bubbles. So it's, again, the color that results from, in this case, the interference of visible light reflecting from two interfaces. Okay, and if it's not obvious what two interfaces I'm referring to on a bubble are, you would just have to think at the molecular scale. So a soap bubble, if you were able to slice open the wall of that bubble and look inside, the soap bubble wall consists of layers. So there's an outer and an inner layer that are made up of soap molecules. And those are, in this little image here, you can see have this sort of red circle with a little tail coming off. This is referring to the hydrophilic and the hydrophobic side of the molecule. Okay, the hydrophilic side, the redhead, you can see is pointing towards what is a water layer that's sandwiched between the inner and our outer layer of soap molecules. Okay, so that's what holds the whole bubble together. And what that sort of structure creates are two interfaces. So on the outer layer of molecules, you can see there's an air interface with water, and then on the inner layer of molecules, there's a water and then the inner air interface. Okay. So the color that we see coming from iridescent soap bubbles has to do with light reflecting and ultimately interfering from those two interfaces. So in this simple schematic here, again showing the soap film with those two interfaces surrounded by air on both sides, what it's illustrating is a ray or a wave coming in and potentially bouncing off of or reflecting off of these two interfaces. So you can see the red reflected wave is reflecting off of the first interface, the air-water. The blue, the origin of the blue wave, is the water-air interface, the inner of the two layers. Okay. The blue and the red waves that are emanating from those interfaces, you can see are shifted in terms of the peaks relative to one another. So this would then is illustrating a phase shift in the light. The phase shift leads to interference. Depending on the nature of the phase shift, we would perceive a different color. Okay? The reason the waves are shifted with respect to one another has to do with the difference in path length. That the first ray here, or the ray that bounced off the second interface, had to travel in order to ultimately catch up, let's say, with the ray that reflected off the top interface. So you can see that a ray reflecting off the bottom had to travel this much further down, reflect, and then travel that much further up. Okay, so the phase shift then is ultimately going to be determined by the thickness of this soap film. And when you look at bubbles, and as you watch a bubble sort of change with time, you'll see the colors moving around the surface of the bubble. And really what that is caused by is the change with time in the thickness of the soap film. So for example, gravity will pull the liquid down towards the bottom of the bubble. Or the bubble will be evaporating at sort of different rates on one area versus another. So you can see the color sort of swirling and changing. So again, the important thing here is light reflecting off of, in this case, two interfaces. When that happens, a single ray ultimately becomes two rays that then can interfere with one another and create that color. So we can, of course, have surfaces that have more than two interfaces that can lead to diffraction. And an example that I'll show here is just the the shiny side of a CD or a DVD. And as we've all done this, as you move that disc in visible light, you see that rainbow pattern that changes as a function of the angle with which you look at it. So if you don't know how a CD or a DVD works, you should realize that CDs and DVDs are actually, it's a polymer, it's a plastic, where there's a continuous groove that's cut from the inside of the disc all the way to the outside. Okay, and so here in this image, you're seeing a scanning electron microscope micrograph of, let's say, a CD surface, and you can see those ridges are corresponding with that continuous groove. When information is written to the disk, so in the image on the left there, it's an unwritten disk. When image is written, or when data is written on the disk, that groove gets broken up into these little islands that you see here, where there are the pits that separate the islands. And these disks are binary, so it's basically all it is a bunch of zeros and ones. And when a laser reads the disk, it's looking for those transitions from pits to raised parts of that ridge, and that's how it encodes and reads, recovers the information. Okay, but the ridges themselves are the origin of that color. And so again, just imagining a light source where waves are coming down and reflecting off the surfaces of that grooved polymer. It's that process of having the periodic structure and having waves reflecting and then interfering with one another that gives you the color change. And so here the distance that is highlighted is this distance between equivalent points in these neighboring grooves. And once again, you can imagine that the path length is different for ray 1 versus ray 2. So there you end up is where the resulting phase shift will come from. But again, in this case now you have many different sources or point sources of light because of all of these grooves that can lead to that phase shift and the color change. And then one more periodic surface structure. This one is more in the biological realm. If you don't recognize what's on the left there, it looks like corned beef to me. And if you've ever perhaps noticed that sometimes shaved meat or cut meat can take on an iridescent kind of color, like this, you might have been disturbed. It actually doesn't necessarily mean there's anything wrong with the meat. And so here are a couple other examples down below where you get iridescence associated with what is muscle. And so this is known on the internet, I guess, as iridescent meat. And it's coloration, again, created by light that is interfering from a physical structure that's made up of bundles of protein filaments. Okay, and again, if you look at a fine enough scale, and once again with a scanning electron microscope, you can see that these protein filaments that have average diameters of, say, 1,000 nanometers or so, sort of line up next to each other, as you can see in the image on the left there, packed together. In the image on the right there, you can see more about the bundles themselves, like so. And what happens then when you shave those or cut that meat at the right angle, you can expose a bunch of surfaces that then, much like a CD or a DVD, can reflect light and lead to that interference phenomenon. So while we're on the sort of biological examples of iridescence, there's been quite a lot of work that's done on iridescent biological structures like beetles and butterflies and feathers and so forth. So I just want to show you some examples of those, which highlight really three what are considered the most important mechanisms of iridescence, which is often referred to as structural color. So a physical structure that's giving the color that's perceived. Okay, so here we'll first talk about some beetles. I guess I'll point out iridescence is usually associated with color that changes as a function of viewing angle. It's not always the case, though. There are what are referred to as angle-independent examples of iridescence. That's beyond what we want to talk about today, but if you're interested, you could look into that further. So there are, again, three mechanisms of iridescent biological colors. We'll just go through them in the order that they were presented in this paper. There's a review paper there referenced at the bottom that goes into great detail about sort of the in the beetle world how iridescence happens. The first mechanism is called multi-layer reflectors. On the inorganic side of things, we would think of this as thin film interference. Okay, so here you've got a beetle that has this, I think it's called a cuticular sort of, let's say, exoskeleton, and you can see that it obviously has very iridescent blue and green portions of color, okay, or areas of color. If you were to take that cuticular sort of, or cuticle, let's say, and slice it open and image it, you would see something like this. And the banding, that dark and light areas of alternating contrast there, are referring to a bunch of multi-layers that ultimately are the source of the color that, again, that we perceive. And so a simple model for that would look something like this. Right, so here the orangish, whitish layers are referring to these light and dark patches here. Okay, they are semi-transparent, which means light is not just reflecting off the surface, but light is going into those layers, and then at each of the interfaces between the layers, some portion of the light is then reflected back. Okay, so here you see, if we call this interface 1, some of the light is reflected off of that. This is, but more continues through, but then again, some is going to be reflected off the next layer, and so forth and so on. Okay. Again, each time this reflection off of these interfaces happens, the light that is being reflected has the potential to then interfere and create a phase shift and ultimately a color. And just like we said before, then what is going to determine the phase shift, at least in part, is going to be the thickness of these layers. Okay. There's another aspect to this that has to do with the index of refraction. So we're not going to talk about that here. You may have heard about the refractive index of a material before. That just has to do with when light enters a transparent or semi-transparent material, it's going to change its, as it crosses the interface, it's going to change velocity. And the velocity change actually changes the angle at which that light ray is propagating. So some of what you see in here, all of these rays going off in different directions or changing slightly as they move from one interface to another, has to do with that refractive index. But for the purposes of our diffraction discussion going forward, we're just going to ignore that. Okay, so that's mechanism 1, multi-layer reflectors. Another mechanism, so here again, this paper is focused on insects. You can see on this sort of brown maroon kind of insect here that there's this band of very, very bright rainbow-like colors. Okay, and the origin of this is a different mechanism from the multi-layer reflectors. Here we're talking about diffraction gratings. So these are periodic surface structures. And once again, if you look at the proper scale and we take a higher magnification, higher resolution image of this, you can see the scale bar is 20 microns. You note how that surface of that, let's say cuticle again, we'll just call it for lack of maybe a better, more precise description, is made up of a bunch of these more or less parallel sets of ridges. Right, that have sort of topographic highs and topographic lows, but are running more or less parallel to one another and are about equidistant apart. Okay, so again, the point here is thinking about an incident wave or light coming in and then reflecting off of these different surfaces, and how it's not exactly illustrated in this, but if you had, let's say, a wave reflecting off of this topographic high and one off of the topographic low, you would get a phase shift. There's another aspect to this that has to do with the color that's perceived. And we're actually going to simplify our model for diffraction so that we don't worry about that. The color ultimately has to do with the fact that in all of these examples, we're thinking about white light. So again, made up of many different wavelengths and energies. But that's mechanism 2, diffraction gratings. So these, again, periodic surface structures, right, where light doesn't have to go, it doesn't have to be transparent. You just have to have the right size and spacing features at the surface to give you the interference phenomenon. And then finally, mechanism 3 is referred to in this paper as photonic crystals. So these are basically the optical analogy of a crystal structure. And on this, this insect here, you can see these really intense greenish, reddish, almost in yellowish areas of the surface. These can actually have different structures that are creating the color. On the one on the left is perhaps most familiar. You have these, what are little spherules that are packed together in very periodic arrays. So essentially like much like the crystal structures we've been making in class with ping pong balls and Vesta and so forth, here's more or less a biological analogy to those. We're not at the atomic scale. I don't know what the scale bar is in this image, but we're talking about hundreds of nanometers in size, certainly. So these kinds of periodic assemblages of these little sort of spherules can give you these intense colors, again, because of the interference created by light passing through or reflecting off of these. You can even put them together in non-periodic ways. So here you've got a bunch of the same kinds of spheres, but you can see they're all randomly aggregated. These actually too can give you iridescence for the same reason, just physical structure that creates an interference phenomenon. And then finally, just as an extension of that, we'll just take a moment and look at a butterfly wing. Okay, so this is another example of a very intense iridescence caused by a physical structure. Here's a macro scale image, digital camera image of a butterfly wing. As you zoom in, you start to see even at this sort of millimeter to sub-millimeter scale, you start to see a bunch of sort of striations on the surface. Okay. If you go even closer, now we're using an optical microscope. You're seeing we're at the sub-millimeter scale now. You see that these surfaces have a bunch of rows of these smaller structures. And then if you switch to the SEM scale, right, and you're looking at these again, but we're still in the sort of hundreds of micron scale, you're seeing these, again, bundles of something, and you have to look smaller than that to eventually see what are very, very faint lines down in here that are maybe too faint for you to see. But if you focus in enough, you'll see that these are made of these very, very periodic arrays of sort of almost rows and columns. It's the substructure that holds these butterfly wings together. And at some point you see you're down at the scale of hundreds of nanometers, right? And it's light both reflecting off of these structures, passing through to the next layer of them, because there's actually layers below this, and then reflecting off of those where, again, you can get that interference that generates the color. And in this case, the color is very clearly in sort of the blue-green portion of the spectrum, right? So that blue-green color has everything to do with the spacings between these different features that are the physical structure. Okay, so in other words, change the spacing sizes, you would change the color that one would perceive. Okay, so that gets us to sort of just thinking about some of the elements of diffraction that are really sort of fundamental in importance, and it has to do with the wave-like behavior of light in terms of interference and phase shifts and so forth, just in a sort of general conceptual sense. Okay, so what is diffraction really describing? Well, diffraction describes what happens when a wave bends around an obstacle. So in this case here, you're seeing some rocks that are different sizes and have some openings between them of various sizes or spacings, right? And outside in the far sort of top of the image, you're seeing a bunch of waves in the ocean. It's very chaotic out there. On the near side, waves that have made their way through these openings are then propagating sort of towards us. You can see in these arcing patterns, right? So waves are bending around these obstacles as they pass through these openings, right? In this case, the openings are all sort of random in size, so we're not seeing any obvious pattern here, right? There are clearly sets of waves coming, but they're not generating any sort of, let's say, interpretable pattern. Okay, that's different when the obstacles in a sort of similar scenario have even spacings between them. So here you're looking down on a beach somewhere. You see these are physical barriers, presumably there to minimize erosion of the beach. Out here you have waves that are coming towards, propagating towards the beach. And then you see that these barriers have a series of openings that are spaced equally apart from one another. Okay, so it's clearly the waves are propagating through the openings. They're bending, so you can see that arcing pattern as the waves, again, propagate towards the beach after passing through the opening. And because of the even spacings, you can see that there's a pattern that's developing, and that pattern is most obvious when you look at the sand, right? So the sand is sort of recording the pattern related to the wave energy and how it's moving sand around over time. Okay, so if you see a pattern like that, you can actually use the pattern to figure out what physical structure created it. So even in an example like this, that would be possible. So the pattern then contains information about things like the distances between the obstacles. So imagine knowing you would be able to use the pattern to work out the distance from here to here, or even from here to here. Okay, and also the orientations of the obstacles. So there are other examples of iridescence that uh, have a sort of additional element that is actually really important for our thinking about diffraction going forward. So there are examples where we observe periodic spot patterns with separation of colors. We now sort of, I think, have a better understanding of where the origin of the colors comes from. So what about the periodic spot patterns? And so here I'll just use an example. When you have a point source of light, like an LED from your phone, for example, if you ever catch a light like that shining off of another screen, like an LED screen, you would see a pattern that perhaps looks something even like this. This is a really sort of perfect example, but you see this periodic spot pattern with separation of colors. Okay, so what is the origin of that spot pattern? And again, it relates to these things we've just been talking about in biological structures especially, is that you have a bunch of interfaces that create many different point sources of light that when reflected will cause interference to occur. Um, Okay, and here now it's not just interference related to the colors generated, but also the positions of these spots in that what is a diffraction image. Okay, so for an LED screen then, which is made up of many, many small LEDs all packed together in a periodic array, you can get a pattern that looks something like the one on the left. And remember, we're not talking about the screen being on. It's a light reflecting, a single point source of light reflecting off of all of these little surfaces here, interference happening, and diffraction taking place. Okay, so that's this is the interference pattern that's created. And this is just another sort of related example, except instead of reflection, now this is an example of transmission, where you get light passing through a physical structure and us perceiving a pattern of spots, and then again the separation of colors. But here I want you to focus more on the pattern that's created, right? So it's this spot pattern where you see these bright lines in the vertical and the horizontal direction clearly you can pick out squares and imagine that the angles between these are 90 degrees. And the reason for that, or the origin of this was an image taken by someone where Venus was in the sky shining through their window screen. And this was the pattern that they perceived on the other side. So again, a point source of light, in this case Venus, very far away, that point source of light passing through a physical structure, right? So in this case, you're talking about a wire mesh where the wires are square. Um, you're getting these square shapes created. The wires in this case are 1.5 or so millimeters apart from one another. But as that light is passing through the mesh, each time it does that, it's bending around either side of those wires, either in the vertical or the horizontal direction. That bending then is creating, each time it's happening, it's creating two new waves that then can interfere with one another. And the interference, which will cancel in some cases the wave or amplify it, gives you this unique spot pattern where the shape of this, again, the sort of square pattern that you see here, relates exactly to the physical structure that made it. So just like the beach example, if you observe the pattern, you can back out what is the shape of the physical structure that made it. Okay, so what do all these examples have in common? I think I've kind of beat on it, but let me just try to summarize. So the patterns and or the colors that are created in these cases is due to the interference of light that is emanating ultimately from many different point sources, and that's caused by the physical structure that's creating that. Most of these examples show this color separation, or this where a very specific color is created. The reason that happens in these examples is because the incident light, the light that's shining on that surface, is white light or polychromatic, right? Which means it's made up of many different energies or colors from the visible portion of the electromagnetic spectrum. That changes with light source. So the sun is white light or polychromatic. A candle would be, made up of many different wavelengths. Any kind of LED or incandescent light would also be white light. They don't necessarily have equal portions of intensity from the different parts of the visible spectrum. So if you put the same object under two different sources of light, the color actually could be different. But that's a little bit of an aside. Okay, so as we go forward, we're going to actually we're going to simplify our model for diffraction. And the way we're going to do that is that we're not going to consider diffraction from white light. Okay, we're going to only work with examples where diffraction is happening because where the incident light is monochromatic, which means effectively a single energy or wavelength. We're going to also consider only when light is behaving elastically. So when a diffraction event happens, there is no energy loss. Okay. We're going to apply interference criteria. We've been talking about that already. But what interference criteria means is we focus on the wave-like behavior of light. So that just means two rays in phase will amplify, and that's constructive interference. Two rays out of phase will dampen, i.e. destructive interference. And then finally, we're really going to only consider diffraction from periodic structures. So like crystal structures or other things, other physical structures that are just made up of sets of equally spaced and equally sized elements. So quick review, and then we're done. I just want to touch briefly on remind you of the electromagnetic spectrum, and one element in particular, since a lot of this should be familiar, just that as you increase wavelength, you decrease energy, or as energy increases, wavelength decreases. In other words, if you remember what Planck's relation is for the energy of a photon, E equals hc over lambda, where hc are just two constants. E is inversely proportional to lambda. So energy, again, will increase as wavelength decreases. Okay, and then just to make sure we're clear, if we're talking about monochromatic radiation, let's say in the visible portion of the spectrum, and you're seeing a bunch of different colored lasers, that means we're taking a single energy or wavelength from some portion of this, the visible spectrum, which ranges from roughly 350 to 750 or so nanometers, going from sort of the deep purple blue to red. Okay, so the next thing I want to just remind you of is the duality of light. So here we'll talk first of the particle-like behavior. So if you have an uncle or someone who likes to build potato guns or other types of cannons, you could perform an experiment that would demonstrate the particle-like behavior, or at least be somewhat analogous to it, let's say. So imagine you have this character here with his tennis ball gun. You build a physical structure, basically a wall, where you have a bunch of solid barriers, but then a bunch of openings, or at least two openings, that would be just wide enough for a tennis ball to pass through. Okay, so we'll just call this a set of slits. Right? And then beyond that, you have a second wall, which we would sort of think of as a detector, but this is where we could record the positions of tennis balls that made it through the slits and then stuck to the wall because it was covered in Velcro. And so what I would ask you is, what pattern do you expect to see on the wall? And if you're thinking of light in terms of its particle-like behavior, I think you would most likely answer that what you would expect to see is, because some balls would not make it through and be bounced off, but others would pass through those two openings, that what you would ultimately get if you fired enough tennis balls at this would be two vertical lines of tennis balls, right, corresponding with the two openings in the wall. And you'd be right. Now, again, because of the duality of light, light also behaves as a wave. So if we took out the tennis ball and replaced that with an electron gun, where you could fire a beam of electrons, again, at something that we would describe as two slits, where, again, you have sort of openings and then areas that would block the transmission of the electrons. And again, we asked, what pattern do you expect on the wall? In the past, people would sometimes say, well, it should be two lines, again, but that would neglect the fact that light also behaves like a wave. And as we just said, as a wave propagates around obstacles, it bends. Okay, so if we just as a reminder, what that means is that if now we're bending light through these openings, and it's propagating forward, it has the chance to interfere. Right? So and this I'm sure is review, but if you have two waves propagating that are in phase, where peaks line up with peaks and valleys line up with valleys, obviously that's going to be a case of constructive interference, where the waves are in phase and amplify. If you shift them by 180 degrees, or half the wavelength, where peaks now line up with valleys perfectly, you're going to completely destroy the wave, and that would be destructive interference. Right? So if we take that example and we just sort of flip it on its side a little bit, and imagine here we have a point source of an electromagnetic wave, right? So that's propagating forward here. We have our set of slits where there are two openings. As that single wave propagates now through these two openings, you've created two new waves. Right? So those waves now are propagating still forward, but have the potential to interfere with one another. So instead of just two lines on the detector, what we actually see is a whole series of bright spots. That is the interference pattern created by those two waves, or even more than that, depending on how many openings or slits we have in our experiment. Okay, so here's just a simple example of video that demonstrates this using just water, or the surface of a pond. Okay, so here he's going to take these two balls that are tied to or held by wires, and just make a wave with one of those, and then add a second wave in that's in close proximity, and what you see is the interference. So just imagine that those are the two openings in the slits, right? So the waves propagating forward from those, or actually in all directions, are now interfering with one another. And you can see that the interference pattern has areas, and they're highlighting them in dark there, where the wave completely cancels. So that's the destructive interference. And then in between those is you can see the high peaks of the wave. That's where they're amplifying because of constructive interference. Okay. And again, if you had a detector at the right spot, you would see a real bright spot here because this is all constructive interference. You would see dark spots here and here because the waves are 100 degrees out of phase, or 180 degrees out of phase, excuse me, and canceling each other out. And again, we're going to ignore the color separation that they're trying to illustrate in this video. Right. So just finally, so this experiment is done in general physics labs. It's called a two-slit experiment, and this illustrates exactly what we showed in that previous slide. I just want to point out some of the terminology you're going to hear going forward. This physical structure, which I was referring to as slits, we'll refer to as a diffraction grating. It's again the physical structure that's going to generate the interference pattern. We often refer to this as being the real space part of the experiment because, again, it's the physical structure. The expression of that in terms of the interference pattern that's created, or the diffraction pattern, is the reciprocal space. Okay, we're not going to get into what reciprocal really means. I just want you to know that reciprocal refers to the expression of the physical structure in terms of the interference of these waves. Okay, so with that, I just would like you to do two things. For Wednesday, I've posted a quiz. It's quiz number 1 on Canvas. It's just a short quiz based on this video. Okay, so please go through and answer that. Try to do it if you can, just based on what you heard. If you need to go back through this lecture, that's perfectly fine. Okay, but have that done by the time class would normally meet at 10 a.m. on Wednesday, 3:25. My plan is for Wednesday is to do a demonstration via Zoom where I will be um, uh, trying to set up an experiment that you normally would do in small groups um, um, as sort of a mini lab. So I'm going to try to do that for you via Zoom using a camera or two. So I'll send around a link for that, but please try logging on a few minutes early. And what we'll probably have to do, my concern is with doing live lecturing is we may have technical challenges. So one way we can try to minimize sort of the load on the internet is by turning off video, at least from your end, and just having the sound and then my video coming to you. So we'll try to work that out in the very beginning. But please be on time. If you can't be there, drop me a note. I'm going to try to record this, but it would be great if as many of you as possible can be there so that we can ask questions and discuss sort of some things about the course going forward. Okay, thanks.